Okay, hello everyone. Yeah, my screen is visible to all of you. Hello, am I
Yes, sir.
audible? Okay.
Yes, sir.
Okay, so welcome everyone to this session on hybrid drones. So generally, we are seeing a lot of drones flying in our localities. And the drones are being used for cinematography. The drone will be used for food delivering. We will see a lot of applications of drone. For now, mostly you can say the drones are used for you can say capturing action images. All the images that you are seeing in your YouTube, Instagram, or all those things that are captured using GoPro or some other type of drones like DJI. So most of them are action cam drones. Okay. Hence, now those are a particular type of drones. But now, since the application of the drone will be increasing, we'll be using the drone to deliver you can say medicines. We'll be using the drone to deliver food items. We'll be using drones to deliver our items. Mostly those are known as delivery drones. Military applications drones are also there. And again, same thing, cinematography drones will be highly developed, and they will be carrying a lot of things along with a very big camera and all those things. So those things can be done using hybrid drones. So what are hybrid drones? We generally know drones that works on battery, but hybrid drones are the type of drones that uses multiple power source. So let's see what are hybrid drones. So generally, hybrid aircraft or drones are unique type of aircrafts that combine the hover capability of helicopter with speed and range of an aircraft. You can see what is the primary difference between a helicopter and an aircraft. An aircraft can't hover in a very confined location. Okay, it can't hover. If the location is very confined, hovering using a, you can say, just 1 second, guys. Hovering using a aircraft, you can generally becomes very difficult. Okay, and if we are using a helicopter, then we can, you can say, hover very easily. If the design is very small, then we can hover very easily. So our hybrid drones will carry the capability of both a aircraft and a helicopter. Okay, it will carry the capability of both a aircraft and a helicopter. Just guys, give me 1 second. Okay, so you can see. So I think there will be no more disturbances. Let's see. So hybrid aircraft or drones are, you can say, they combine the hovering capability of a helicopter and speed and range of a aircraft. So these are our hybrid drones. Hybrid drones are based on fixed wing airplane and quad rotor structures. You can see they have fixed wings like this, and they also have quad rotors. Okay, they also have quad rotors. Okay. Now we define those structures as H-stall and V-stall. So what is H-stall? It is horizontal takeoff and landing. That means the takeoff is horizontal and landing is also horizontal. Okay, this is landing and this is takeoff. Okay, so you can see horizontal, landing and takeoff. Those are known as H-stalls. Then we have V-stalls. What are V-stalls? V-stalls are vertical takeoff and landing drones. V-stalls are vertical takeoff and landing drones. Okay.
Sir, your voice is not audible and the screen is off.
Sorry, there was a problem in my internet connectivity. Okay, no problem. So I'll be starting from where we have left. Okay, so H tall and V tall. Okay, H tall and V tall and hybrids. So let us discuss about these various types of drones. Okay. So first is flight mode. In hybrid drones, what is the flight mode? In hovering mode, hybrid aircrafts behaves like a helicopter and can vertically take off or land. Okay, you can say in hovering mode, hybrid aircrafts. In hovering mode, that means when they hover, when they want to hover, just like your helicopters, they vertically take off and they land vertically, while your aircrafts, they take off horizontally and land also horizontally. So when we want to hover our drone, let's say for same thing, for cinematography, for capturing action videos or action images, and for, you can say, surveillance, generally we use drones that can hover in a small region. So for those things, for you can say, for you can say, if we want like that, or if we want our drone to be used like that, then we switch on the helicopter mode, or you can say vertical takeoff mode. The transition mode is the flight regime of converting from helicopter to airplane. Okay. The transition mode is the flight regime that converts from helicopter to airplane and vice versa. So transition means, remember, if the drone is hovering, suddenly it will not switch off its rotors and it will start, or it will switch on its vertical rotors. It will not be switching off its vertical rotors and it will switch on its horizontal rotors. That will not happen. These are vertical rotors. Okay. They rotate vertically. Okay. These are vertical rotors. These are horizontal rotors. Okay. They rotate horizontally. So the drone will not be starting the vertical, or it will not be switching off the vertical rotors and it will start on the horizontal rotors. That is a continuous process. Continuous process means slowly the vertical rotors, we can say, power will be drawn from the vertical rotors, and the power will be slowly the power will be increased in the horizontal rotors. So that is the transition mode. So we have to know about transition mode. It is not just like an abrupt transition. Okay, it is not a abrupt transition. Okay, it is a slow transition. Not slow means it will not be taking 3, 4, 5 seconds. Okay, transition is slow as compared to other type of agility that is there in the drones. Hybrid drones, in forward flight mode, the aircraft is a fixed wing airplane that offers a wide range of speed and maneuverability. Now you can say that if we switch on the aircraft mode, then the speed in which the drone can move, it increases a lot. Okay, it increases a lot, and the maneuvering ability, that means how it can maneuver, it can take swift turns. Okay, remember, a aircraft cannot rotate much faster, but it can take swift turns. Okay, so the drone cannot do this type of maneuvering. Okay, it cannot do this type of maneuvering. Okay, so a drone can take swift turns, it can rotate, it can, that means just like a jet plane. If you have seen a jet plane, you can say rotating a jet plane is a very difficult task actually, but you can see the maneuvering ability of a jet plane. That is a aircraft. Hybrid drones are mostly used in military applications, agriculture and surveying. Okay. Then there are different types of hybrid modes in our drone. Generally, fuel source. That means if our drone is using fuels, then what are the type of energy generation units are there? Ramjet, ramming will be done. Pistons, small, you can say your V8 engine or Rankle engines will be provided. Then turbo means your you can say, what I will say, turbo means your compressors. Okay, you can say turbines. Turbo means your turbojets or turbines. Then in piston, we have reciprocating and rotary. Reciprocating is just like your inline engines, okay, or V engines that is reciprocate. Then there is rotary. Rotary is a Rankle engine, is a rotary engine. Turbojet, turbofan, then turbo propellers and turbosaft. So these are types of drones that uses fuel. They can use diesel, petrol, diesel, or mostly refined kerosene that is used for most applications, you can say aircraft applications. Then we have hybrid. The hybrid, they have structures like parallel and series structures. Okay. And also they have series, parallel, complex structures. Generally, they have what? What are the series and parallel? You can see they have both the energy source of a engine and a battery. They have both the energy source of an engine and a battery. So parallel and series means the engine and the battery will be in parallel. Series means the engine and the battery will be in engine means, or engine means it's a small engine, very small engine. Okay. Engine means it's a very small engine. And full electric, complete electric, power supplies, EMS. Okay. Then motors are there. Power supply, you can say in small or in full electric drones. Generally, we have lithium batteries, we have fuel cells, and we have, or there can be solar power. Then in motor driven, we can have permanent magnet synchronous motor, brushless DC motor, and superconducting motors. Okay. So these are your drone divisions based on their power source. Now, pure electric propulsion. A UAV, unmanned aerial vehicle platform, is a critical part of mission execution. And generally, UAV vehicle consists of energy flight control systems, power propulsion systems, communication modules, and engine energy management systems. So you can see these all components are there in a drone. Okay, flight control systems, power propulsion systems that will supply, that will. Hello. Okay, someone's mic is on. Wow. Okay, then there are communication modules, energy management systems. Okay, so we have to energize, or we have to supply power to all these units. So how to do that? So in pure electric aircraft, the batteries generally supply energy mainly used to maintain all the UAV systems and loads, while the energy management systems controls energy distributions. In electric propulsion systems, high energy density and low loss converters are used to achieve the system's energy management and motor control. So this low loss converters means, generally, in order to control a motor, we use what? We use inverters. Okay. We use inverters to control a motor. Why? Because our battery supply a constant voltage. Okay. Our battery supply a constant voltage. 12-volt battery, it will always supply 12 volt. Okay. It will always supply 12 volt. Now, how to reduce the potential? By inserting, or by, you can say, increasing the resistance. Okay. By increasing the resistance. Now, remember, when we increase the resistance, generally most of our power is lost as heat, because we want our system to run, but we are decreasing the potential and we want a lot of current by the use of resistance. That means we are able to drop the current, but since we require a lot of current in our motor for enough torque, our most of our energy will be lost as heat. Okay, this is the reason why we don't vary the potential using resistors. You can consider, sir, variac, we can use variac, variable resistors, okay, in order to control the voltage. And why do we need to control the voltage? It is because the motor's RPM is controlled by the voltage, while the motor's torque is controlled by the current. So in order to control the RPM of your drone propellers, we have to increase or decrease the potential, but your battery supplies constant potential. So how to do it? One option that comes in our mind is using a variac, that is a variable resistor. But a variable resistor will, you can say, it will dissipate a lot of heat. That means most of my energy power from the battery will be lost as heat in these resistors if I use variac. Hence we use high frequency switches, and the average of those high frequency switches, generally, you can say, creates a varying, you can say, potential. Okay, they creates a varying potential. Okay, so this is the reason why we need to use inverters. So those are your low loss converters. You can say that this is the reason why we need low loss converters. Okay, and are usually required to achieve the system's energy management and motor controls. Often unidirectional and bidirectional converters are used in the middle of power supply and the DC bus to accomplish the battery charging and charging controls. Okay. We can say UAV often uses permanent magnet synchronous motor as power sources, and because of their high efficiency, high energy density, high speed, reliability, and ease of control, those are mostly the choice of motors in any drones. Okay, those are the choice of motors in any drones. Now, mostly the power flow diagram. Okay, let us know about the power flow diagram of a drone. Okay, so generally we have a energy management system or power source. First is the power source. The power source, then there are various types of converters. DC to DC converters are there, and our inverters are also there. Okay, DC to DC converters are also there, and our inverters are also there. Then we have DC bus. What is the use of a bus? Bus is generally used to, it is used to convert a lot of signals. If you have a lot of signal inputs, you can use a bus in order to create a single output of all those signals. Okay. That means a potential of 0.31 volt has to be applied across some of, you can say, most of the electronic components. So generally bus is used to distribute the terminals, okay, or distribute the circuits, distribute this potential across the circuits. Then we have inverters. As I have said, inverters are high frequency switches that helps to control the RPM and current of the motor. Then we have motor control that controls the inverter and motor. This is the feedback, remember. All the blue ones are the feedback channels. Okay. All the blue ones are the feedback channels. So what you can say, your energy management system controls the converter, directly controls the converter, and your motor controller is there that controls the inverter. Then it is connected to the gearbox. This is for both HTOL and VTOL. Then fuel propulsion systems. The fuel propulsion systems of a UAV generally consist of a fuel supply system, engine, mechanical transmission, and propellers. Okay. In the system's structure, engine is the core of fuel propulsion system, playing the role in energy conversion and UAV power supply. Generally, we have a small engine of some 60cc, 70cc engine or 80, 100cc. Okay, engines will be there. 100cc is even, it is very good, very high. Okay, so it should be used in a, but for big drones, we can use 100cc engines. For small drones, we can go for 10, 20cc engines. Okay, small engines. Okay, now, then fuel engines can be classified into two categories, piston and turbine. Okay, that means we can use a piston engine or a turbine engine. Okay. Generally, how turbine engine works? Turbine engine also uses the same principle. There will be an engine that will rotate the turbines, or there will be a motor that will rotate the turbines. Either through battery, you will be rotating the motors, the motor will be rotating the turbines in order to generate the required thrust, or there will be a rotary engine that will run the turbines in order to generate thrust. So you have to run the turbines through some rotating unit, either an engine or a, you can say, motor. Okay, but generally your piston engine is directly connected to the gearbox and output. Okay, so there will be a fan that will generate thrust. In your piston engine, you need a propeller, not a fan, sorry, not a fan, a propeller. Okay, you need blades, propeller blades to generate thrust. But in turbine engines, generally engine will be used, but the thrust will be produced by the turbine blades because of compression and expansion of the air modules. Engines suitable for UAVs need to have many characteristics, including long endurance, small volume, high power to weight ratio, robustness, and ease of maintenance. Okay. There we can't rev gasoline 100cc engine continuous for long times. See, no one is saying to use the bike engine. Okay, bike engines are very different. If you say a bike engine cannot be revved for long time. But the engine that will be used in a drone, it will have its own cooling system. Okay, and you can run on full potential for any number of time that you want. If you see MotoGP, you can actually rev an engine. Okay. for any number of time or any number of time that is required. Okay, so they drive at full potential, MotoGP drivers. So engine can run for a long. You can see your generators. Generators, they will be running for 8 hours, 9 hours continuously in full potential. Do you see those engines fail? No, they don't fail. Okay. If you say about bike engine may fail. It will, I think it will not fail also. If it is still, it will, if it is continuously run for a lot of time. Okay. Okay. Then a fuel drone power supply diagram. There will be a fuel tank. Then the fuel will be supplied to the engine. Engine will run. There will be a gearbox and there will be a propeller. This is the basic diagram of a piston engine drone. Okay. A basic diagram of a piston engine drone. Now comes our turbo engines. Remember, turbo engines, but they will be driven by an engine or a motor. We can use turbines. Generally, the thrust is being generated by the turbine because of the airflow. The way in which the air is, you can say, inducted and exhausted. Because of that flow, generally thrust is generated. Okay, generally thrust is generated. What we do, generally we compress the air. Okay, we compress the air and then we ignite it if required. We ignite it also. Okay, when the compressed air, then we spray the fuel and we ignite it. But we need a mechanism that will rotate. Okay, rotation won't be happening automatically. We need a mechanism that can help it to rotate. Once rotation is done, then we can induct air. We can increase the density of the air. Okay, and also we can mix the fuel if needed. If you can say enough thrust is needed, then we can also mix fuel. Okay. Yes, they are being used. Okay, your hybrid drones, military application drones, they are using these turbines. Okay. Then turbojets are there, turbo fans and turbo propellers and turbo fans. Okay. You can say combustion chamber. You can say combustion chamber in here, but they have to rotate. Someone has to rotate. You can see there is a power shaft in here. Okay, someone has to rotate it. Either a motor or a drone. Oh, sorry, motor or an engine will rotate it. Okay, so let us compare the speed. Now here comes the main thing. Your piston or rotary engines will achieve a speed of only 110 to 260 km/h, but your turbojets, they can achieve a speed of 700 to 1100 km/h. Turbo fans, they can achieve a speed of 500 to 1100 km/h. Okay, they can produce an output of 560 kilonewtons. These are very large drones. Okay, hence this much amount of weight is required. Okay. Then turbo propellers are there, turbo shafts are there. They can generate this much. I can say they can generate a lot of thrust to reach this type of speeds. Then finally, the electric hybrid propulsion system. The development of a fuel propulsion system for a UAV is becoming increasingly mature. Okay. Because electric propulsion systems are available. So the fuel propulsion systems are no more needed, because if you will be installing a small fuel tank, a small engine, how long you think it will last? It will last for just 1 hour. But if you use battery instead of that, then it is good. And also you will not be having vibration because you are using battery. So if you will be using motors, a lot of vibration will be there in the drone. Remember, drones are used for certain application. Like if my drone will vibrate, I can't install a camera or I can't capture a good image or a video. Okay. Only when I'll not be buying a drone just to fly it. Okay. Depending on the type of instruments that are, you can say, mounted on the drone will have the application. If a camera is mounted on the drone, it will become an action drone or a surveillance drone. If sensors like IR sensors are mounted on the drone, then you can say it will be same mapping and surveillance drone. If you can say spraying, you can say insecticides are insecticide spraying unit, if it will be mounted to the drone, then it becomes an agricultural drone. Okay, so various types of drones are there depending on the type of instruments that we mount on them. Okay, so this is the reason why fuel propulsion systems propulsion engine can be used, remember, but they are increasingly mature. Mature means only in a specific areas this fuel propulsion system can be used. Like agricultural drone, they need a fuel propulsion system because a lot of torque is required to lift that much amount of weight of the pesticides as well as the you can say tanks, okay, that will contain the pesticide. However, with increase in depletion of petroleum resources and climate problem,
Hi.
the traditional fuel systems can no longer meet energy and environmental protection needs, while the pure electric propulsion system is still under development. The problem of a battery energy density, sorry, the problem of battery energy density restricts its further application, resulting in PEP system that is not full, that you can say that fully meeting the need of air transportation. Okay, you can say clear. It is fully meeting the need of air transportation. That means the batteries that we're using, there is also a problem in using the batteries. The batteries that we're using, it doesn't have enough energy density to run a drone for 4 hours, 5 hours continuously. For agricultural drone, even the battery is not sufficient to generate enough torque for a long amount of time because of the battery energy density confinedness. Okay. People have purposed fuel electric hybrid propulsion system as the solution. What is fuel electric? That means it will have both a engine and a battery connected in parallel or in series parallel or in complex hybrid. Just like your hybrid electric vehicles. In your hybrid electric vehicles, you have an engine and a battery, and there are various types of hybridization in your electric vehicle, like parallel hybridization, series parallel hybridization. So let's just study what are these. So in a parallel hybridization, you can see the engine is also connected to the gearbox. The motor is also connected to the gearbox. That means the engine and the motor simultaneously can run the gearbox, or only engine can run the gearbox, or only motor can run the gearbox. So depending on the requirement, either to use the power from the engine or to use the power from the motor, it can be switched. Okay, it can be switched. This is your parallel hybrid system where the motor and engine are connected in parallel. Okay. Then we have series. In series, there will be a fuel. Then engine will be there. Engine will be connected to a generator. Okay. And the generator will be connected to a motor. Okay. It will be connected to a motor. So generally, your in
Sir, audible ಇಲ್ಲ.
okay. So you can see a fuel and engine will be there. Then the engine will be connected to the generator, and the generator will be generating the required current to run the motor. So this is an efficient way. Remember, if we use engine and motor in parallel, actually parallel combination is less. That means it is bit less efficient than a series. Why? Because we know that engine never runs on their full efficiency. That means the engine efficiency is nearly 40 to 50%. If you go for F1 vehicles, their engine efficiency will be somewhat 50 to 60%. Okay. Why? Because a lot of energy or power is lost in friction and vibration and heat also. Most of the power is lost first during the combustion process. Some of the power is lost as heat. Then the power will be lost as friction in the rotating parts. Then the power will be lost as vibration. Okay. So engines cannot run on their full efficiency. But if engines are not connected to drive line, okay, if the engines are not connected to drive line, then obviously some of the efficiency that was being decreased because of friction and inertia, it is eliminated because the engine is now connected directly to the generator. It is not connected to any drive line. Okay, so this is a, we can say, very efficient design. Then the generator is connected to the motor and the motor to the gearbox. So this is parallel. Okay, in here we'll also have a battery. You can say battery is there. So the engine will run the generator and it will recharge the battery, and the generator will also run the motor. But when the engine is not required, let's say battery is full, the battery can run the motor. Okay. Then series parallel hybrid. Series parallel hybrid means we can use the motor as series and also as parallel. Why? Just see the power flow diagram. In the previous model, you can see fuel, engine, motor, battery. There is no recharging unit, but sometimes we use small generators, or these motors can also act as a generator. Okay, you can see two-way sign is there. That means battery will run the motor will act as a generator, and it will run the battery. Okay, so that is also done. So that is not this is series parallel hybrid system where we have an additional generator. The motor is not used as a generator, but can be used. But the power flow diagram, you can see it is only in one direction. Previously, in here, the power flow diagram was on both the direction. Okay, that means the battery can run the motor can act as a generator and run the charge the battery. Okay, but in series parallel, we have a generator. That means the engine, okay, the engine through mechanical coupler can run the generator without running the gearbox, and the generator will go through the power converter and it will recharge the battery, and the battery will again through the power converter will run the motor and it will run the gearbox. Okay, now the same mechanical coupler can also, you can say, we can also direct the power like this. So both it is acting as a series as well as parallel. So when the power flow is towards the generator, it is acting as a series hybrid. When the power flow is towards the, I can say, gearbox, then it is a, you can say it is a parallel hybrid. Okay. Complex hybrid. Complex hybrid also uses the same type of architecture. Only the algorithm that controls the, you can say, uses of engine and the motor, they are more efficient. Okay. The algorithms that are used for the, you can say, controlling the engines and the motor, they are a bit efficient, more efficient than the series parallel hybrid propulsion. Okay. Then you can see the structure types. So series, the propulsion system is powered by electric motor only. Simple structure, easy to control and low cost. That means the propulsion system is powered by electric motor, and the electric motor is powered by the engine. Okay, remember, in series, the propulsion system, that is the propeller, it is run by the motor, but the motor is run by the motor battery and the engine. This is a very simple structure, easy to control and maintain and very low cost. But disadvantage is high emission, low efficiency, only has electric mode. Okay, that means only the motor will be driving the drone. So we can't use the drive power of the engine. Parallel, the propulsion system consists of an engine and an electric motor working together to generate power. That means both of them will be running the gearbox to generate the power. High max power, have fuel and electric mode, high reliability, greater performance at high speed. Okay. Then high emission, low efficiency, short endurance. They have these parallel hybrid drones are very reliable. They have a very good performance, but their time span, that means they will not run for a longer period of time. Then we have series parallel. Integration of series and parallel structures can work in a single or dual mode respectively. High efficiency, again, in here the efficiency is very high. So out of these three, you can see a parallel has low efficiency, parallel mode, and a series mode also has low efficiency. But if we go for series parallel, both of them are there, then it becomes very efficient, very reliable, long endurance. But the structure becomes very complex. That means we have to use small planetary gearbox in order to, you can say, control the power output from the motor and engine, or to couple the power output from the motor and the engine. Then controlling is very hard, cost is very high. Okay. Then a converter has been added to the series parallel. Okay, complex. Complex means a converter is added to the series parallel to independently power the motor. Okay. So in a complex hybrid, we can power the motor independently. Actually, the algorithm is a bit complex. Okay. High efficiency, again, it has a very wide range of operating conditions, better performance, complex structure, more difficult control, and high cost. These are some of the advantages and disadvantages of having a this type of drones. Okay, then the system design. Okay, so I'll not go into the details of the system design because mostly the system designs you can know when you go for a full course, because I have to say you about PID controllers. Okay, what is PID controller? PID means proportional, integral, and derivative controllers. Okay, proportional, integral, and derivative controllers. So all the drones will have this type of. If a drone has a certain amount of intelligence, mathematical intelligence, okay, then you can find out that intelligence, or you can know that that intelligence is because of this PID controller. So what is this PID controller? So PID controller means your proportional, integral, and derivative controller. So what is a proportional control? Remember, when you want to perform an action, okay, when anyone performs an action, so that action depends on three things. First is how to perform that action, that is the present. Okay, now we also have performed that action previously. So now you can say, uh, sorry. First is when to perform the action. That is where to perform the action is present, how to perform the action is past, and when to perform the action is future. That means whenever you want to perform an action, you generally take into account three things: your past, future, present, and future. Okay, when you want to perform an action, any action, let's say you want to drive a bike. So when you want to drive a bike, you use your past experience to drive. You use your present knowledge of the environment to drive. Let's say you are driving a vehicle. That means you have gone for a holiday to let's say Goa. Okay, and there you just bought or you just rent a bike. Let's say a uh, interceptor. Okay, you just you can say rent a interceptor. Now you are able to drive the interceptor because already you have driven the bike previously, or those type of bike previously, and you can also drive the interceptor in Goa because you are able to understand the surrounding, present surrounding, and also you are able to drive the vehicle correctly because you know how to move. Okay, where to reach at what location or at what time. So, to perform an action, generally three things are taken into account: your past, present, and future. So, this PID controller acts on these three things. Your proportional controller, P for proportional. So, P for, sorry, P for proportional. Proportional, I for integral, and D for derivative. Okay, proportional, integral, and derivative. So, what is proportional? Proportional means acting or controlling a signal in present time. Integral means you can say knowing the past values of the signal and tuning the signal, and or controlling the signal. Derivative means to predict what will happen to this signal in future and control the signal. Okay, remember, just understand this architecture of PID. So there is an input signal. This is your input. Okay, input signal, just like your acceleration, you have in your drone, you provide the inputs through your remote control. Then there is a drone controller. Then that drone controller actuates the drone. Actuates means either it has to increase the RPM of the motor or it has to decrease the RPM of the motor. Okay, those are your actuators. Those are your output of your input. That means when you provide the input through your remote, then the input, that input signal passes through all these controllers. Okay, PID controllers. Then they excite the, or they run the actuators. Okay, so the actuators rotate the motor, or they either increase the speed of the motor or they decrease the speed of the motor. Okay, now those actuators will have sensors. Okay, sensors, and they will provide the feedback. So what is this feedback? This feedback, in here you can see input is xt, but the input to the controller or the PID controller is et. What is et? It is the error. You can see xt is your input. Okay, x dash t, sorry, this is x dash t. X dash t is your input and x of t is your output. So your error is what? Your output minus input. So x of t minus x dash of t. This is my error in the whole system. Now the PID controller acts on the error. It uses the current situation to, by using the proportional value, to act on the current situation on the error, because it uses the current situation and provides the certain amount of proportional gain to the signal. Then integral means integral, generally it uses the past values of the signal. That means what has happened previously for a given amount of, for a given type of signal, so it uses the past value. Derivative, it predicts the future value of the signal. Okay, let's say this is a signal, a continuous signal. Okay, this is a continuous signal. The signal, you can see this is the point at time t. It has started from time t is equal to 0, and total time t is equal to 10 seconds has elapsed. Once now it is 10 seconds. So how to perform on the 10th second? It uses proportional controller. Okay, then how the signals were there previously, to know about those things and to tune the signal, it uses integral controller. And how it will move forward? Okay, by finding out the slope, we can find out the derivative gain, and it will control the future value of the signal. Okay, so this is your proportional. Okay, so you can say these are the three controllers: proportional, integral, and derivative controllers. Okay, so have a small amount of knowledge on this PID controllers, because you have to know some amount of mathematics, okay, in order to know more about PID controllers. Okay, but PID controllers are the best type of controllers that you can see. Okay, now machine learning controllers are there, but PID controllers are very good controllers. Okay, but if you want your drone, that means if you want to drive your drone in market area in a whole lot of situations, then machine learning drones are very good, but PID drones are very good for a given type of environment. Okay, then controllers. Let us discuss about drone controllers. The drone controllers consist of a bunch of different PID controllers. Okay, various types of PID controllers will be there for controlling the thrust, for controlling the roll, for controlling the yaw. So what are these thrust, roll, and yaw? Okay, let us come back to our drones. Okay, you can see. Okay, let me just draw the axis system of a drone. Okay, just one minute. Controllers. Okay, so let's say this is my drone axis system. Okay, this is my drone axis system. This is my z axis. This is my x axis. This is my y axis. Okay, so if the drone is rotating along this x axis, okay, this is the forward motion of the drone. Okay, this is the forward motion of the drone. So if the drone is rotating about x axis, then it is rolling motion. If the drone is rotating about y axis, it is pitching motion. If the drone is rotating about z axis, it is yaw. Okay, roll is rotation about x axis, pitch is rotation about y axis, and yaw is rotation about z axis. So for each control, for pitch control, roll control, and yaw control, along with throttle and other type of controls, PID controls are used everywhere. Okay, PID controls are used everywhere. Okay, the PID controllers are responsible for stability, angle correction, and manual control. Displacement PID controllers for navigation. Like when you switch on a home mode, how the drone should fly to you, that is controlled by a PID controller. The drone controllers has a complex design in order to deal with different types of PID controllers. Let us just see the diagrams. Okay, will not. This is a mathematical model. If you can say in Skyy Rider we have a 1 month nearly, you can say 1 month of drone design course. Okay, we have a 1 month of drone design course. Okay, where we completely develop a 3D model of the drone, and we develop the controllers for the drone, and we test the drone in a given environment. Okay, so this is the MATLAB model. So stabilized PID controller. What are stabilized? It means these PID controllers will already be tuned, and it will be installed in your drone. It is responsible for maintaining the drone for a given position from manual controllers. It consists of 3 PID controllers for 3 directions: roll, yaw, and pitch. Roll is along x-axis. Okay, roll is along x-axis. This is forward. These are x, y, and z. So roll is along x-axis. Pitch is along. This is roll. Okay, pitch is along roll. Okay, L. Pitch is along y-axis, and yaw is along z-axis. Okay. The angular controllers are fed from the pilot joystick by the target position. Excuse me. Okay, clear? What are the use of PID controllers? Then these are the architectures of PID controller. Okay, we'll not go into details of these architectures, but these are the architectures of your controller. Okay, body frame controllers. They generally control the yaw, pitch, and roll of your drones. Okay. Then PID controller design, how to design the controller. There is a cascading drawing. You can see this is the controller that we have designed. Generally, we design these things in MATLAB or any other you can say computation tools. That means where we can use this type of toolbox or we can write codes to design this controllers. Okay, so that is what it is written. The controller is fed by desired position and actual position. So generally input is there. This x star is the input, x of t is the output from the this is a feedback from the sensors. Okay, so x is the input, output is this t of t is the input to the actuators, and the actuators again relay the signal to the back to the sensor where the error is calculated. That means input, what is the error between the input and output signal? Okay, input and output signal. So error is generally x of t minus x star t. Okay, that is your error, e of t. Clear? Then system model. We can say these are your transfer functions. Okay, I will be saying if you, that means if you have studied about Laplace transform, I think most of you, if you have done, if you have done the engineering, then you know about Laplace transforms. So those Laplace transforms are used to convert your differential equations into algebraic equations. Okay. They used
తీసేయి
to
వస్తా
convert your
అన్నాడు
differential
రాలేదు మళ్ళీ
equations to you can say
వచ్చి
algebraic
వెళ్ళిపోయాడా
equations.
రాలేదు
Okay, hello, some of your mics are on. If you can mute yourself. Hello. Okay. Then these are the transfer functions. Okay, that uses Laplace transform. So I'll not go into Laplace transform. Just remember these are the transfer functions of your this is the whole transfer, complete transfer function of the model. Okay. Complete transfer function of the drone model. Okay, remember we develop the transfer function of the drone model and we mathematically solve it so that we can have very good PID controllers. Okay. So these are the graph of PID. You can see how the PID will try to control. You can see in here how it is achieving stabilization. If there will be any type of instability in the drone, so with time how it stabilizes those inputs. Okay. So PID tuning. So generally proportional part, it generally you can see the first responsiveness for error is done by the proportional. That means if there is a tree in front of it, then the proportional controller provides the maximum value for the signal. Like if we have P and we have I and we have D. Okay. So if we need first response, then the value of the P will be highest, 5. Okay. It will be 0.1. It will be some 0.01. Okay, this is the settings of PID for, you can say, first response. Then for a stability, okay, for a certain type of stability, your proportional controller will have very small, or you can say it will have low input. Your integral will have more inputs. Let's say it will be having 0.7 and your derivative will have also have input of 0.3. Okay, now if your drone is trying to overtake, okay, it is just stabilizing. Now if your drone is trying to overtake, so what is the path it should take? Now in here it has to predict the path. Okay, it has to calculate the path. Again the proportional will have very low value, integral will also have low value, overtaking differential or derivative will have high value. Okay, so by this type of settings for a fast response, that means you are just you are going to hit a tree. So how to maneuver? Okay, so for fast response, that means just increase the thrust, you can say very fast, your proportional controller value will be highest. For stability, integral controller value will be highest. Okay, then for, you can say, path prediction, your differential controller will be highest. Okay, this is what it is shown in here. Then this is the communicator architecture. Generally your two processors are used for, one processor is your you can say energy management unit, another processor is your whole control, total control of the drone. Okay, Okay, so let us again review of what we have discussed. So drones, what are the various types of hybrid drones? What are the architectures of the drone? Then pure electric, fuel and hybrid drones. Then sorry, turbo drones or hybrid drones. Then yeah, the fuel electric architecture. First is the remember first one is the pure electric, then fuel propulsion, then hybrid drones. In hybrid drones, we have this type of segmentation: parallel hybrid, series parallel hybrid, and complex hybrid. This is the diagram, power flow diagram for parallel hybrid, power flow diagram for series hybrid, power flow diagram for series parallel hybrid, and complex hybrids. Okay. Okay, it will be ending at actually, let's see when it will end. So this is the comparison of various types of architectures. Then how to design the controller architecture. Okay, this is the board architecture. This is the mathematical architecture of the controller along with transfer functions. Then some of the graphs that shows how the controller is stabilizing the system. Then tuning the PID to get the maximum of your PID controller. Okay. So now we'll be having the question and answer session. If you have any question, you can ask. You can either type out the question or you can ask the questions. Hello.
Your voice is breaks.
So quickly ask your questions, or else I'll hand over the session to Idisri.
Good evening, sir.
Good evening.
This was a good presentation. Actually, I really
your
would
voice
like.
breaks, sir.
Yes.
I
So
would.
if you have any question, ask.
Yes, sir. I would like to ask if it's possible to obtain this PPT.
Sir, your voice is breaks, sir.
You can obtain this PPT actually. Okay, I'm just giving you my number.
Sorry.
Text me. Okay, I'll be uploading this PPT to you. Okay, generally, I'll be sharing with you that you can only watch the PPT. Okay, you cannot download because that is not means allowed. Okay, you can watch the PPT.
Okay,
but
sir.
you can edit it. Okay. So this is my number. Just text me. Okay. Hello. Sorry.
Hello, sir.
Yes. Hello.
Sir, your voice is not clear, sir.
Permissible capacity of a drone.
What? Yeah, what?
Load carrying capacity of a drone.
So there are mainly various types of drone. If there are micro, mini, okay, micro drones, mini drones, okay, then medium sized drones, then large size drones, then okay, these four categories are there. So micro, generally small drones that carries camera are your micro drones. Then mini drones, you can say they can carry a big camera. Okay, they can carry some other stuffs, like they can carry food. Medium sized drones are used in agricultures. Okay, or medium to large size drones are used in agriculture. So if I say micro, I'll just say the approximate can carry approximate weight of 1 kilos or less than 1 kilo. Okay, micro drones. Mini drones, they can carry load up to 5 kilos. Medium sized drones, they can carry load up to 30 kilos. Large sized drones can carry load up to 80-90 kilos. Okay. Clear? Hello?
Yes, sir. Yes, sir.
Yes, sir. Sir,
Okay. Anyone has any other question? Yes, quickly ask.
how to use for drones, sir?
Hello? Okay. Okay. So if you have no more questions, then I'll be handing over the session to Itisri. Hello, Itisri. Are you there?
Yes, sir, I'm there. Thank you for this session.
Okay. This you can take over the session.
Okay.
Okay. So I'm Okay, so thank you everyone.